Okay, YouTube, in this video we're going to introduce the concept of a linear system, or at least a system of equations, okay? So let's go ahead and begin by looking at the definition. We say a system of linear equations in two variables, that is, x and y, usually consists of two equations of the following form. And I say usually because sometimes you have like maybe two or more. You could have 3 or 4 equations, but usually we look at a system with two variables and two equations. And I say also usually because these equations are given to us in standard form. Sometimes it's not a crime, but if we have linear equations, we could have an equation that's written in slope-intercept form, okay? But looking at this, we say it's usually in this form where these happen to both be in standard. So what makes a system a system? Well, when you think about systems of things, systems are complex things, okay? They're not very simple parts. They're a bunch of parts put together. So we're saying a system is something that consists of 2 or more equations put together. And our goal when we explore systems is really to look for solutions to a system, okay? So let's go ahead and now define what we mean by a solution of a system of linear equations. So we say a solution of a system of linear equations in two variables is an ordered pair x comma y that satisfies each and every equation in the system, okay? So we say that is when we plug this xy back into both of these equations, all the equations in the system, it makes them true. We get a true statement. So we basically value solutions to systems so much because solutions to systems are common solutions to every equation in the entire system itself. So we know that when we were to, if we were to graph, say this line right here, go graph this line, what we would be seeing is the collection of all the points that when we substitute it back into that individual equation make them true. We're looking for now solutions that make both of these true at the same time. Everybody in the equation or system true at the same time. So really quickly, what I'd like to do is just kind of show you how can we verify if an ordered pair is a solution to a system or not. And really all we need to do is plug it into each equation in the system to see if it satisfies it. So really quickly here, we've got this equation here, 3x minus 2y is 2. So I'm going to say 3x minus 2y is 2 where I've removed x and y and we're going to replace them with these values here that we're given. So a 2 for x and a 2 for y, and we're being asked, is this ordered pair a solution to the system? Well, when we evaluate this, we get 6 minus 4 is equal to 2, which comes out to be 2 is 2, so it certainly evaluates the first equation. Now, that is not good enough to say that it's a solution to the entire system. We also need to check it into the second equation here. So we'd say x plus 2 times y is equal to 6, where we're plugging in 2 for x and 2 for y, so we get 2 plus 4 is 6, and we can easily see here that it's also a solution to this. So this is very important. We would say that this is a solution to the system of equations, but it's a solution to the entire system because it made all equations in the system true. My question now is 0 comma negative 1 also a solution to this system? So we're just going to check it the same way. We say 3x minus 2y is equal to 2. I've taken out the values for x and y, and we're going to substitute in 0 for x and negative 1 for y. So evaluating this, we get 0, and a negative 2 times a negative 1 is a positive 2. So again, easily we can see that this one is satisfied. But again, I want to point out that's not good enough to say that it's a solution to the entire system. When we plug this into the second equation now, which was x plus 2 times y is equal to 6, then what we find out is when you plug this in, we actually get negative. Oops, that's a negative 1. It's a negative 1, everybody. We say this negative 2 is equal to 6, which is not true. It's not true. It's not true. So we would say that this is not a solution to the system. So that being said, what I want to be able to do is, given a system of equations, how can we very easily go and determine what the solutions are? And one way to do it is just guess and check. You could plug in infinitely many xy pairs until you find one that works, but it's not very feasible. Of course, we don't have an eternity to do this. So one thing I did mention is this. If we were to, say, go graph each of the equations in this system, each of the individual equations graphs, its graph contains all of the points x, y that satisfy its own individual equation. So of course these are two different graphs here, but what I want to point out is 2, 2 satisfied them both. So what must be true about this point 2, 2 with respect to both of these graphs? And I would say that it would have to be true that this point would have to be on both graphs of the equations, or at least where the two graphs intersect. So we have a method for solving a system of linear equations, and that first method is very, very basic and primary. We refer to it as the graphing method. So we say determine which of the following ordered pairs is the solution to the system in two variables here, two equations in two variables, and then verify our answer algebraically. What we're going to do is instead of checking these individually, I want to know which one is the solution by graphing it. So step one is just to graph the equations in the system. That's all we're going to do, okay? So we'll start with both of these. They're both in intercept form, or sorry, not intercept form, but standard form. So what we're going to do is we're going to find their intercepts. That is how we quickly graph equations in standard form. So I'll go ahead and get ourselves set up here, a lot of commas. But what we'll do is we'll plug in 0 for x here and find the y-intercepts, and then we'll plug in 0 for y and we'll find the x-intercepts. So starting with this first equation, when you plug in 0 for x, you would get this statement here, negative 2y equals 4. And if we divide both sides of this by negative 2, we would have y equals negative 2. So we'd say that its intercept there on the y-axis is negative 2. And if you plug in 0 now for y, you would say, well, then 4 times x equals 4, where if we divided both sides by 4, we would get x is equal to 1. So first things first, get my pen tool back out here. Seems that whoa. Thanks for being patient with me here. Hopefully I can get this to work. Not really sure why it's doing that. There we go. We got an intercept of 1. So if we go graph this now, we say 0, negative 2 is on this graph, and 1, 0 is on this graph. I'm going to go ahead and connect the dots here as best I can. And you want to use a straight edge. If you were doing this by hand, you need to use grid paper. So now looking at the intercepts on this second equation, if you plug in 0 for x, then we get the statement 2 times some number is equal to 6, and that number must be 3. So we get 3 as our y-intercept, and looking at our x-intercept now by plugging in 0 for y, we get x is 6. So I'll go ahead and graph these out. We say 1, 2, 3, 4, 5, 6 is going to be about right here. I'll try to move this to the side. Here we go. There we go. That's better. So 6, 0 on our x-axis, and then 0, 1, 2, 3 up here, and we'll sketch this in as nicely as we possibly can. So our first step there was just to simply go ahead and sketch the lines. Now our next step, number 2 here, is going to be basically this. Look for any point of intersection. Point of intersection, okay? And I kind of see one here on the right. I kind of feel like that this point right here is a point of intersection. So what I kind of want to speculate is 2, 2. You know, I can't just guarantee that it is, because sometimes these points run into each other at decimal values. So since we want to be sure, the third and final step in the graphing method essentially is this. We're going to check the ordered pair. Now the thing was, we were given a couple of ordered pairs here, 2, 2, and negative 2, 4. I think at this point, negative 2, 1, 2, 3, 4, that's right here. We would see that if we check this, it actually might come out to be a solution to this first equation, or at least it was the second equation we graphed, but it's not going to be the solution to the system, because we say solutions must be at points of intersection. So system solutions exist at points of intersection of our graphs, okay? So that being said, I just want to check 2, 2 here, and so I would get 4 times x minus 2 times y is 4. Plugging in 2 and 2, I get 8 minus 4 is 4, and that's true. And plugging 2, 2 into the second equation, I get x plus 2y is equal to 6, where we have 2 and 2, so I get 2 plus 4 equals 6. So that is indeed our solution to the system. So before we're done with this video, what I want to do is comment on what would happen if you had a system where graphs never intersect, or they always intersect. And what we start to see is we have different types of solution sets. It is possible, if I have 2 lines that never intersect, think about what would be true about their slopes, or at least their graphs there, to make that true. But if they never intersect, then I would have no solutions to the system. Or if I had 2 lines that were exactly the same line, they would overlap at every point, and we would get solutions to the system that are all real numbers. So since we're solving systems of linear Qs, linear equations, and because solutions to systems occur where graphs intersect, it follows that sometimes we're going to get infinitely many, or we're going to get no solutions. So really quickly looking at these examples, and then we'll wrap it up by kind of describing them over here, we would say that 3x minus 2y is 6. Quickly graphing this here. Let's go ahead and start with the first equation. We say EQ1. We want to write down its intercepts. So plug in 0 for x and 0 for y. But if we were to plug in now 0 for x here, we would get negative 2y equals 6. So that means that our y value would be negative 3 for its intercept on the y-axis. And if we plug in 0 for y, we would get the statement 3x equals 6, which makes its x-intercept equal to 2. So our first equation here has 2 intercepts. It has an intercept on the x-axis at 2 and a y-intercept of negative 3. we're going to carefully graph this in. We want it as straight as we possibly can. So here's our first equation right there. And then our second equation, 6x minus 4y is 12. Let's find its intercept. So we say EQ2. And if we were to plug in now 0 for x and y respectively, plugging in 0 for x in this equation gives us negative 4y is 12. So in other words, we get negative 3 as our y-intercept, negative 3. And if we plug in 0 for y now, we get 6x equals 12 is our statement. That means that our x value must be 2, dividing both sides of that by 6. So we get 2, 0, and negative 3, 0. And I really, maybe I could do this. I could switch over to like an orange, yes. But you would see that these two equations overlap at every single value that they have in common there. So we would say that the solution to this is all real numbers, okay? We would also say infinitely many solutions, infinitely many solutions to the system. So what we're going to do here is we're also going to classify this as being a consistent system. When you hear me say a consistent system, it means it has at least one solution, but we're also going to refer to these as being dependent. And the reason why I think of this as dependent, this is how I remember it, is they live together. They depend upon one another. Whereas when we looked at this example over here, we would classify this as consistent because it had at least one solution, but we'd say that these lines are independent from one another. So in terms of key vocabulary, consistent means our system has at least one solution, or infinitely many. And whether they're independent or dependent depends upon whether they share all solutions or just one. So now looking at this last example here, we say that 2x minus 2y is 6. We'll go ahead and list our intercepts for equation 1 here. So we'd say I've got my y-intercept and I've got my x-intercept, and we'll go plug in 0 and 0 respectively. I plug in 0 for x. Then I get this. I'd say negative 2y equals positive 6. So dividing both sides here by negative 2, we get negative 3 is its y-intercept. And by plugging in 0 for y, we get its x-intercept is a positive 3. So let's go ahead and graph this. We say 0, negative 3 is down 3. That's its y-intercept. And then 3, 0 is over here. So we get this line with the slope of 1, sketching it in very carefully, very straight with a straight edge. And then we say equation 2. Equation 2. We would say that if we were to find its intercepts here, 0 and 0. Let's go ahead and plug in 0 for, let's say, x. So if I plug in 0 for x, I get negative 2y equals positive 2. So y is negative 1. So I get negative 1. And then if I were to plug in now, this is supposed to be a 2. Let's switch this here. 2. If we plug in 0 for y here, I get 2x equals 2, which gives me a positive 1 here. So what we end up with is this. If we go graph this, we get negative 1 as our y-intercept and positive 1 as our x-intercept, but we still get a line that you notice has a slope of 1. So these are our two equations here, and what can be said about them in terms of how many points of intersection exist here. And we'd say no points of intersection. So we say that this system has no solutions, okay, and we would refer to this as an inconsistent system. So when you hear consistent, it means you have a solution. Inconsistent means you have none, okay? So we could also comment that they're parallel lines. So last thing I want to do here is kind of break each one of these system situations down. So we say if a system of linear equations has one solution, then we'd say graphically the graph of the system is a pair of non-parallel lines that intersect at one point. So what I'm going to do down here is I'm just going to draw in like just a basic general graph. I just made this up. But we say we have two equations that meet at this point right here. And we'd say that that right there is one solution where they intersect at only one point, okay? Furthermore, we say the system has exactly one solution, x, y, and this is the example sketch below. But what about infinitely many solutions? Well, we saw an example of this over here, but in terms of graphically interpreting it, it says the graph of the system has two parallel lines, but that overlap everywhere, okay? I shouldn't say parallel here. Basically, they are the same line. So we say that the solutions are all points that are shared by both lines, or all real numbers. And so a graph of this would look like this, and just to emphasize it, I will draw like a dotted line over the top of it. We'll say one graph is dotted and one is not, but they are the same line. And there are infinitely many solutions, okay? And then last but not least, no solutions. We say the graph of the system has two parallel lines that never overlap. So we would say that a system that has no solutions, that is inconsistent, would look like this right here. And we'd say that these are parallel lines. Cheers.